horizontal asymptotes, we want to talk about the things that we've already said in class, where if you replaced it with infinity, where would you find it? You know, and go through those pieces. So the graph of any rational function f of x over g of x has the following characteristics and behavior. Asymptotes. Those are going to be our horizontal asymptotes. Cassie was just asking about that in case you didn't hear it before. When we're finding those horizontal asymptotes and we want to write those down as far as end behavior goes, that is end behavior. You know, those asymptotes are supposed to be where those branches are going to as you go further and further to the left and out to positive infinity to the right. Now this end behavior stuff, like I said, we're above this at this point. If the degree of the top is less than the degree of the bottom, the horizontal asymptote is 0. And if the degrees are equal, well then we use the fraction in front. But this is what I mean by we're ahead of the game on that. If we look at that, we should say to ourselves, well, what would happen if we put infinity into each of these? Well, the infinity squares would cancel out. And so it's going to approach y equals 3/4. You know, that's what we want to be able to do. If the degree of the top is greater than the degree of the bottom, there's actually a couple things we can do. In fact, the first thing that we learned how to do was do the division. Get it into that nice y equals a over x minus h plus k format if you can. Or do the division so that you can figure out what is an asymptote for this graph. And if that can't be done, like it says, we rip it apart and do the division, then there's not going to be a horizontal asymptote. So we would put no asymptote. But that kind of bothers me that it's still using that Algebra 2 thing of there is no horizontal asymptote. Not a horizontal asymptote, but we are going to talk about a slant asymptote today. And remember, asymptotes are things that our graphs will approach, but they're never quite going to get there. And any additional asymptotes we can get keep us from having to grab the graphing calculator. That's what we want. So vertical asymptotes, those occur at the real zeros of the denominator. We know we can't divide by 0, so we find those right away and say, here's where they are. And x-intercepts. To find the x-intercepts, what we're doing is we're trying to figure out where would y be 0. Almost looks like Jackie. All right, so x-intercepts are where you set the y equal to 0. And in order for y to be 0, the numerator has to be 0. So that's why it says these occur at the real zeros of the numerator. And then the y-intercept is if you put 0 in for x, what do you get? So it's always the opposite. So we hadn't had any practice on this, so like I said, without the practice, if you couldn't remember how to do this from Algebra 2, then yes, I would hope that you would stop and just hang in there. So x-intercepts and y-intercepts, kind of little pieces we're going to tack on today, along with slant asymptotes. Pardon me. And everything else we've done up to this point. Lots and lots of good stuff. So where do we go? When graphing rational functions, you should find all the asymptotes. Like I said, we really just want to grab the graphing calculator for nothing, if we can get away with it. But if there are pieces that we can't find algebraically, then we'll grab the graphing calculator. So vertical asymptotes, horizontal asymptotes, end behavior asymptotes, like they're saying here, it's one that we haven't experienced before called slant asymptotes. That's what we want to look at. And let's look more in depth at the case where the degree of the numerator is larger than the degree of the denominator. Now, they're right in saying no horizontal asymptotes exist, but they're leaving out that slant asymptote possibility when they say that. So we have finding the asymptotes and the intercepts of this function. We want to know everything we can possibly know about it before we do any graphing on the graphing calculator. So, bless you. The first thing you're going to notice, at least I hope, is is, hey, that denominator is factorable. And those zeros of the denominator become our vertical asymptotes. And they are lines, so we write them as vertical lines. X equals -3. And X equals 3. And then horizontal asymptotes, well, we've got the degree of the top is greater than the degree of the bottom. And like it said, then we normally put no horizontal asymptotes. So, horizontal asymptotes, none. But that doesn't mean that there isn't something helpful in that. Because we can do this division. This degree is smaller than this degree. We can actually divide it, and that's what we need to do. Because that's going to give us a marvelous little thing called a slant asymptote. That helps us out a lot. So we have our little x squared minus 9, and we notice, hey, there's nothing behind it, so it doesn't hurt to put the 0x squared, the 0x, and the 0 on there. That generally helps the people, you know, feel like they're finishing through this problem. So we have x squared minus 9, and we know we have to make that front term match. So we would use an x to get that to happen. And that would give us x cubed minus 9x. Now it did its job. We have an x cubed.
Do you have to do long division? Or since you can separate it and get x?
We do have to do long division because it has to go back to, was it originally a linear factor? And it's not an original linear factor.
Okay.
So we change the, well, x is working, we'll put that up here. We change the signs and add. And we realize we can't multiply x squared times something and get an x term. So this is our remainder. Right there. So what does that mean to us? Well, ignoring the remainder, this will be a slant asymptote. So look at that. Well, it's just x. What is that? It's the line y equals x. So we have a slant asymptote. At y equals x. So let's just go ahead and get all the asymptotes we have so far. We've got the two verticals, and then we have the slant. And just like anything, for presentation, label as you go. Make sure your helper lines are just dashed or dotted. Never solid. Do you remember where the line y equals x goes? Perfect diagonal through first and third quadrant. It's a separate thing. It really is a separate thing. And the book doesn't mention it, but then in some of their examples, they actually do go through and show you how to get it, which is kind of silly. So, kind of weird that they left that information off of there. So now, that's what we have so far. We want more. And that comes from the fact that we haven't found the intercepts yet. So, when we want x-intercepts, the y has to come out to be 0. That's what has to happen. So I think, okay, I go back to the beginning here. This is y. I can't have zeros in the denominator because that is where my asymptotes are at. So how do I get y to be 0? If the top, the numerator is 0, this will be 0. So it would have to be 0, 0. We put a 0 right here. This is going to become 0 divided by -9. We will get 0. So the numerator equaling 0 gives you that x-intercept. If you wanted to do it algebraically, you could just set x cubed equal to 0. You could take the cubed root of both sides and get x equals 0.
How does the x-intercept work if there's a slant asymptote going through that?
And that's because, just like horizontal asymptotes, slant asymptotes may work for portions of the graph, but not the whole thing. It's always that middle section of hyperbolic functions where things can get a little weird and they can actually cross those horizontal and slant asymptotes. Y-intercept, that one's easier. You just stick a 0 in for x and see what you get. So, if we went back up here to the original and put zeros in for x, then we'd end up with 0, 0 again. So our x-intercept and our y-intercept on this one are going to be at 0, 0. So we got one more piece of information. We know our graph is going here, and then my next step would have been talking right about what Art was saying there. What if it lands on your asymptote? If it lands on your vertical asymptote, you are wrong. You are flat out wrong. You either did your vertical asymptote wrong or you did your intercept wrong. If it lands on a slant asymptote or it lands on a horizontal asymptote, it better be in the middle of your graph, because the middle of the graph has behaviors that don't necessarily fit the hyperbolic branches. And what we're doing when we're finding all of this information is finding the behavior of the hyperbolic branches. So, now, since that's all we could get algebraically, we would grab this bad boy. I was going through these over the weekend, and I was making tables, and I came in and asked, wait a minute, were we going to make them do all this by hand tables, or were we going to have them do the graphing calculator? Ah, we said graphing calculator. So, we can just use graphing calculator. But make sure you use parentheses so your calculator knows, take everything on the top and divide it by everything on the bottom. Zoom 6, so I've got negative 10 to 10. And we use the table feature and get some points here. And the good news is we can see our vertical asymptotes are correct. We see an error message right there. So now, for the rest of the graph, we have -4 and -9 and a little bit of change. And then we have -5, -7.8, -6, -8. That's all I would need to grab from the table, because here's what I know. Those branches must approach the asymptotes without ever touching them. Here's an asymptote right here, here's an asymptote right here. Has to look like that. Absolutely has to. Now we'll go to that middle section. We have -2, 1.6. -1, and just a little bit. And of course our 0, 0 is correct. It's always good to know that your math is matching. And this is symmetric. And again, approaching those vertical asymptotes. Smartboard's not oriented. So it looked like it crossed there. And then a little bit for the other branch. The same thing, where once we figure out where that local minimum is, kind of curve back around, because we know that that slant asymptote is going to work along with the vertical asymptote to direct us for those hyperbolic branches. So when it says find the asymptotes, we're not just talking vertical and horizontal anymore. If it is possible to find a slant asymptote, you need to do that. So how do you know? When the degree of the top is greater than the degree of the bottom, do the division. Yes.
For the homework, do we have to write down all of the points we just used, or can we just
on the test, you know, you really should show us what you were doing in the table for presentation points. But on the homework, I'm okay with, as long as you found all of this, you should be able to make a really good sketch of what it looks like. So, did we do everything? Find the asymptotes and the intercepts and graph the function. Got it all. So, for this particular one, what type of asymptotes did we have? We did have vertical. Vertical and slant. And if the end behavior asymptote is a slanted line, we call it a slant, or some books will call it an oblique asymptote. Oblique just meaning that it's not perfect. Oblique technically means like it's off, and that's what's happening here. It's not perfectly horizontal. It's not perfectly vertical. So when no horizontal asymptote exists, how can you tell what type of end behavior your graph will have? You use your slant asymptote. Use your slant asymptote. Well, especially, remember, for the branches, this is going to work. Your slant asymptotes, your horizontal asymptotes definitely work for the branches. With hyperbolas, that's a big win. The middle is something we'll deal with as we go. All right, so, like I said, we're doing a lot of graphs on steroids, where the graphing part isn't necessarily the most difficult part because we're using the graphing calculator, but the rest of this is the math that we need to do. So analyzing the graph of a rational function, find the intercepts and asymptotes, and use limits to describe the behavior at the vertical asymptotes, and analyze and draw the graph of the rational function. So get everything you can out of this algebraically first before we go on. All right. So my hope is we've got something factorable down there. Is that factorable? What are the factors? So -3 times 2 gives us the -6, and when you add them together, you get the -1. So what was that really helpful as far as finding? What piece of information? Vertical asymptotes. So what are they going to be? Again, write those equations as lines. We've got x equals 3 and x equals -2. Horizontal asymptotes. Big oval. Because we could cancel out one of these, but it's still infinity. And if you're looking at this thinking, well, won't that cancel out? No, no, no. Don't even, that's spitting in the ocean, remember. It's these leading coefficients that are going to show us what we need. So as this gets bigger and bigger, this number gets bigger and bigger, and that gets us closer to 0. Now, if you're the memorized type, you're looking, okay, in that chart it was, if the top is less than the bottom, it's y equals 0. Yes, you could memorize it that way too. All right, so, oops, not x-intercept, horizontal asymptote. All right, x-intercept is when would we manage to get a 0 for the y? What number could we put in this that would give us a 0 for the y? For the y. Yeah. Go to the numerator. That's where we look. It has to be a 1. So this graph is going to cross the x-axis at 1, 0. Now the y-intercepts, we're going to put a 0 into the thing and see what we get. So if we go back up here, this is the easiest place to put it, because this is going to be a -1, and this is going to be a -6, and we're going to get 1/6. So going back to the original makes it a little bit faster when we're trying to find y-intercept. All right, now it says use limits to describe the behavior at those vertical asymptotes. So that's one of those things that, you know, some people will wait until after they have it graphed, and you can do that. But one of the other things you could do is just put in some numbers to get a feel for where the graph is going to go. And quite frankly, we let you do that either way. But our asymptotes, because I just scrolled up here, we said we're at 3 and -2, so the least we could do is get them ready. The limit as x approaches -2 from the left, and the limit as x approaches -2 from the right. And then the other one was a 3, so the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. It did not say an overall end behavior. It said, describe the behavior at the vertical asymptotes. But we do down at the bottom anyway, I think. Isn't there, do you guys have
Yeah.
a slot down at the bottom? Yeah. So we are doing the analysis. All right, let's put on what we know. Vertical asymptotes at 3 and -2. Horizontal asymptote. And a couple of points. Our points were 1, 0 and 0, 1, 6. Ready for your GC? That's what we could get by algebra. X minus 1. Again, you have to use parentheses so the calculator knows. Take all of x minus 1 and divide it by x squared minus x minus 6. There it is. Grab some points. We need a little beyond -2, so -3, -4 would be good ones. -3, -2/3. In actuality, that's probably the only thing I need for that branch. I know what the branch is going to do. That's what the asymptotes are there for. But if it's a test, we're going to put a few more down. So that allows us to fill in one of these limit notations. Which one? -2 from the left. So -2 from the left, where's it going? Approaching -2 from the left, -infinity. I didn't leave myself enough room to write my little -infinity. Okay. All right, let's get some more for the middle. -1, 1/2. Got the 1, 0 that we already knew about. 1/4. And then the overall look, you could go back and say, oh yeah, this one was the kind of S shape. So that allows us to fill in 2 more. -2 from the right. What do we put? Yep, 3 from the left. All right, and the last little piece. Looks like so. So the limit as we approach 3 on the positive side. Coming in. And infinity. Still a lot of blanks to fill out about this thing. Man. Are we using all the X's? Which ones do we have to leave out? Negative 2 and 3. So we're coming in from negative infinity. We hit negative 2. We jump it. Go to 3. And we jump it. Are we using all the y's? Look at all 3 parts. Are any of those parts going to use all the y values up and down forever? Middle section. And here's where it gets Remember we said we were going to force all of these to be continuous over their domain. So what numbers would we have to leave out in order for this to say it's all reals for its domain? Negative 2 and 3. Yeah. So all x not equal to negative 2 and not equal to 3 will make it continuous. If you take those numbers out of the domain, then this is a continuous graph. Increasing and decreasing. Let's see if we have both or if we just have one. So we read graphs from left to right. Decreasing, decreasing, decreasing. It's decreasing. Then we have to tell them where. Well, over the entire domain. So we go back to the domain and we just copy that. Read them left to right, and that's what they're asking for. Increasing, decreasing is what's happening from left to right. All right, is this puppy symmetric? We got an even or an odd thing going here? It actually isn't odd. Because if you look at what's happening at 1, 0, and then negative 1, and what was that, 1/2 up there? It's not going to work over the origin either. So this is a no. It's not going to happen. It's not perfect symmetry. Bounded. Cut off above, cut off below. Oh, we got arrows pointing in both directions. No. Local extrema. Turning points is what they're asking. Is there any obvious place where it was going up and now it's going down, or it was going down and now it's going up? It has to be an obvious change. These are all gradual. You don't get any of those either. So now the end behavior, the overall end behavior, that's back to our limit as x approaches negative infinity. Our graph is doing this. And our limit as x approaches positive infinity, our graph is doing this. So you have to grab a part of the graph that would go to the left forever and ask yourself, where is this going in terms of y? What are we approaching as we go to the left forever? Yeah. That horizontal asymptote is 0. How about if you go to the right forever? Yep. That's what that horizontal asymptote. Again, for the branches, that horizontal asymptote is working. Whew, that's a lot of stuff, isn't it? We're going to do it again, and again, and again, and again. All right, find the intercepts, analyze, and draw the graph of the rational function. Well, this time, even the numerator is factored in. I'd want to do that. Denominator, difference of 2 squares. And we've got that difference of 2 squares thing going big time. Now, when everything's factorable like this, you should really ask yourself about holes before you get going too far. Does this one have any holes? It doesn't. Do you remember where you're looking for holes? That's when one of those factors will cancel out, or maybe even more than one. If there's a factor that's going to cancel out, then that's going to happen. So let's go after it. Vertical asymptotes would normally be what we do first. Where are they at? X equals 2 and x equals -2. Okay, then normally we'd go after horizontal asymptotes next. Think about infinity. 2. Yep. Infinity squared over infinity squared would drop out. -2, -4 is spitting in the ocean, so we need the 2. All right, x-intercepts. What would make our numerator 0? Both. Both. That's why it's important if you can factor the numerator to do so. So we would get 1, 0 and -1, 0 as x-intercepts. Well, we're only going to get one answer if we put x in for 0 there. -2 over -1. And we get 1/2. So we know we're going to have to do the limits for asymptotes. Before I go there, though, should we be checking for a slant asymptote on this one? When do we get slant asymptotes that will be helpful? When the degree on the top is greater than the degree on the bottom. Right. We already know about y equals 2. Now, it wouldn't hurt. I mean, if you do the division, you're going to get y equals 2. You will get the horizontal asymptote. So horizontal asymptotes and slant asymptotes are kind of linked together, and we want to make sure that we're constantly checking. Are we going to get any new information by doing the division? Alrighty, so we're going to need to approach 2 and -2. Yes, we do these. It's part of the analyze. It is.
So we have to do all of the limits, all of the intersects and stuff for every single question?
For the homework, no, I don't think they have you do everything. I think it's just specific. Right. I think they don't have you do some of these pieces. Yeah, but we need to know they exist, and we need to know they're out there, and we can find them. All right, let's get those asymptotes on there, huh? And our intercepts. Slow down since this is going slow. 1, 0, and -1, 0. And 0, 1/2. Okay. Now, I'm going to take this just one step further here, all right? Because what we want to do is get as much information as we can without necessarily having to use the graphing calculator. So the question really is the branch supposed to go here or is it supposed to go here? So one of the things you could do is just put a number 6 or so. Put a number into the original equation and just check to see, is it positive or is it negative? If it's positive, is it up here or is it in this section? And then, we get a really good idea where they're going to go. But that's for another day. We're going to talk about all these pieces eventually. Like, this isn't enough. We're going to add some more little pieces to this as we keep going. So we've got our parentheses, 2x squared minus 2 parentheses divided by parentheses x squared minus 4 parentheses. So it looks like our middle section there is pretty good. Just want to make sure we're approaching those asymptotes. And then we can see that obviously these are both going to be up in first quadrant here, but we need some points to deal with, so -3, 3.2 would be good. And that really would be enough. On a test, I'd probably grab one more point, maybe put the -4, 2.5 on there. Sure, dips into that corner. And then the 3 and the 4 on the other side. So, and then we can go back and talk about our limits. And those vertical asymptotes. As we approach -2 from the left, what's happening? Come in from the left side on -2. Where's your graph going? How about from the right-hand side? +2 from the negative side. Left side, down. +2 from the right-hand side. Up. So we have both of them. Whew, and still more blanks to fill in. Domain, what do we have to leave out? -2 and 2. Range. Look at your Y's. There's a group of Y's right there. We are not there. And we have to let them know that. So we're -infinity up until there. Now, it looked like that was our 0, 1/2 spot. But we can't take that for granted. And we know that without calculus, we can't find it. So what we would do is we let Linky tell us, is that actually the highest spot right here? And yeah, the Y value is 0.5, so it is 1/2. So we're doing -infinity to -1/2. Oh, sorry, +1/2. Was 1/2 an actual value on our graph? So this is the first time we've had U-square brackets in a long time. It is an actual point on a graph. And then we take a hop. Where do we start up again for Y's? Yeah, on the other side of 2. Remember, that was our horizontal asymptote. We can't use 2 though, because it's an asymptote. So we make that jump and then we start up again at 2. Continuous over all except, which ones we leave out? 2 and -2. I probably just write all x not equal to +or -2 on that. Increasing and decreasing. Did we get lucky and this one's the same? Yeah, we've got both this time, don't we? Increasing, increasing, oops, decreasing, decreasing. So we're going to have to chop this up into intervals. We'll have some increasing and we'll have some decreasing. So, INC here. Increasing, first branch, right? -infinity up to what? -2. And remember, these are always parentheses because you can't be increasing and decreasing at once. Where's the other spot where this is going to be increasing? To 0. Remember, that was our high spot, 0, 1/2. Now, don't unionize that. Don't put a union in there. We're saying from here to here it's increasing, from here to here it's increasing. If you have to put something there, write the word and. Here and here. It drives you nuts to do that, or a comma or something. Decreasing. The other branch, and yeah, the other half of our middle piece there. So that started at 0 and it went to what? 2. then 2 to infinity for the other branch. So that one took a little more thinking than the last one. Even or odd? This one is even. It is being reflected over the y-axis there. Bounded. Remember, bounded means both above and below. Is it bounded both above and below? No. Because it has to be for the overall graph. And you could say portions of this, but that's not what they asked. They said, is this graph, the overall graph, is that bounded? Did we find extrema this time? Yeah, we had a local max right there in the middle. So a local max of 1/2 at x equals 0. Overall in behavior. Brain's getting ahead of my hands today. All right, as we go to the left forever, what's this graph going to approach? 2. Yeah, that was our horizontal asymptote. How about as you go to the right forever, does that change? Still approaching that asymptote 2. It's impressive, people. I mean, if you look at that and you think, wow, and I understood all of that? I can make all of that happen just by looking at this thing? Well, we can at least get a start. Sue, analyzing graph. 5x plus 21. That does not look to be a factorable nice thing, right? How about the denominator? Is that a factorable nice thing? Oh, that's an extra nice thing, isn't it? That's a perfect square trinomial. X plus 5 squared. Vertical asymptote. With that denominator, figure out what would make that a 0. Horizontal asymptote. Your infinities. All right, so x-intercept, how are we going to get our y to be 0? Now this one actually requires, you probably want a little bit of algebra. You set this 5x plus 21, that numerator, equal to 0, and you find it. So you subtract 21, and you divide by 5. Y-intercept, put your 0 in for x. What do you get? This will be a 0, this will be a 0, this will be a 0. 21 over 25. We don't exactly get beautiful fractions with this one, do we? It's just kind of nasty. All right, so let's set up our limits with the only vertical asymptote we have here, which is -5. We put on the limited information that we have. X equals -5, -21/5 0, so -4 and a little bit more 0. And 0, not quite 1, 21/25. This is a weird one. You definitely would want to see this one. Let me get this in. painting a pergola. You can see there's no symmetry here. This is just really, really strange. So there's our -5. -6, -9, -7, -3.5, -8, -2.1. Oh, I could put my horizontal asymptote on there. Yeah, I didn't want to rule that. And then the other side, we'd be putzing with a little bit. I'm just going to make a quick sketch for today. We'll come back to this tomorrow. That's Cassie's doing exactly what we need to do next, which is we have to find that local max, so we can get that high point. But we'll start there tomorrow. So good news, you're doing graphs for this assignment. No. That is no. I'm going to give you the new assignment. That is not right because we were initially going to do this in 2 days. That is absolutely not what was on day 2. You must have changed it and not saved it or something. It is 23 to 30 and 32 to 35. I know. They're supposed to be changed. Like I said, we changed them last year because we knew we didn't get that far. So you can just put them on the same sheet of paper if you want to. Well, go back and take a look and make sure that all those asymptotes are right. So if you already did them, basically you don't have